It's a pleasure to welcome Jamie Taylor, and he's going to talk about construction of two-dimensional convex shapes for excluded volume. I'll go like this when you're 40 minutes.
Okay. So thank you for the introduction, and I'd also like to thank all of the organisers for giving me the opportunity to talk here today, and of course all of you for coming to see this. So as the talk title gives away, this is going to be on the construction of two-dimensional bodies from their excluded volumes. So I have the good fortune that we've had a lot of talks on liquid crystals already today, so hopefully I can sort of skip through the introductory parts on that a bit. But also that Peter gave a lovely talk earlier where he was talking a lot about steric interactions between hard particles, which is again a big foundation on the type of work here, and by no coincidence it was when I was working in his research group in Kent that we started looking at these types of problems. So as he mentioned, the short-range hard interactions between rigid particles tend to be sort of messy compared to long-range attractive interactions. And the point of this talk is to try and say, okay, in this very, very idealized, simple case of two-dimensional convex bodies, can we say something about how to compute these excluded volumes, and can we go backwards and say, I want this to be the excluded volume, what kind of shape should we have? So just for that outline, we'll do a little bit of background, then talk about this forward problem. I'll call the other one the inverse problem, because the inverse problem is always the hard one, and it's a lot harder. And then I'll show you some pictures and implementations, and then wrap things up a little bit. So for some background. So pneumatic liquid crystals, these are states of matter that typically have non-spherical particles. You're talking about long things, rods or whatever. And these systems can form phases which have no translational correlations, over long distances at least, between the centers of mass of your particles, but over long distances you may have orientational correlation. So in essence, your particles have no distinguished center of mass, but they may have a very well-defined orientation. And these things are useful in all sorts of applications, the most obvious one being probably your phone screen would be an LCD. So in the case of this kind of system, we just have a rigid particle. It has no sort of internal degrees of freedom apart from its orientation. How do we describe this system? Well, in the simplest case, where we're just going to try and look at the bulk behavior, so we're not thinking about defects or sort of continuum elastic theory, we're just going to look at the bulk part of the energy. We can try and describe our system by a probability distribution function, which just tells you the probability of a particle having a particular orientation. As I say, we're not going to care about the centers of mass because we're looking at sort of translationally invariant systems. So in 2 dimensions, angle is straightforward. We just have a simple scalar quantity. And if we're then going to go into the sort of statistical mechanics of such systems, then the first non-ideal contribution to the Helmholtz free energy is something like this, which may look familiar from Peter's talk. So if f is going to be your distribution function, which tells you the probability of finding a particle with a certain angle, you have this double integral term here. So rho 0 is the number density, so this is how many particles you have per volume. And this thing here, Ex, is a kind of interaction energy which depends on the relative angle between your particles. So this entire expression is really just summing up all of the pairwise interactions that you have between all the particles in your system. And because this is the sort of lowest order non-ideal term, this is the one that contains quite a lot of information, and this is really the sort of cornerstone of the Onsager theory, which chops off the series expansion at this point, and all the phase behavior of your system can really be encoded from this double integral term here. Now this Ex term, you may think it's a bit suggestive. In our talk it's going to be the excluded volume. So in the case of rigid hard bodies, the only thing that turns up here is the excluded volume, which is the amount of space excluded to one particle by another given their orientation. Okay. So just to give a little picture of this, distinct from the ones we've seen before. So just to be explicit in this case, I'll use a curly M to signify a body in 2 dimensions. Everything's going to be convex. And then Ex of theta m, this is going to be 2 versions of particle m at relative orientation theta. Okay? So if we have a simple system of 2D rods, this is somehow the easiest thing that you can work with. What we can do is say, okay, we'll put rod 1 here and rod 2 at some relative angle, and we're going to try and move this little rod around in space and see how much space we can't access. And what you see is that this little red dot, its center of mass, will trace out some parallelogram, and you can just straightforwardly compute that the excluded volume, or I should really be saying excluded area, is just L squared times the absolute value of sine theta. Okay, so this is one of the nice cases where you can really explicitly write it down with no problems. Now, if you want to look at more general shapes, you're going to get into a lot more complicated things very, very quickly. As Peter said, you can have various approximations, but the sort of completely correct answers are normally very difficult to find. And it's going to be hugely dependent on the type of shape that you have. These are sort of very geometric objects. But one formula which is universal, this even holds if you're not looking at convex bodies, is what's been called the Mulder formula before. So you can always write the excluded volume as this is the difference in terms of sets. So you take everything from one set, everything from the other, take them away and make a new set. So it's not the set difference. R theta is the rotation by angle theta. So you take your body, you minus another copy of it, rotate it, and then look at the difference between all the points in the two. So this set here is going to be this parallelogram here. So the total excluded volume, which is just a scalar, is the size of this set. So you can write it in this way. And as I say, this was derived by Mulder in 2005. So this gives us, at least in some sort of principled way, a method of calculating the excluded volume for particles. But now, okay, we have an expression. Let's try and make it a bit more tractable. The way that we'll try to make it tractable is... Oh, sorry, I've jumped ahead a little bit here. So now we know what the excluded volume is. I'll just reiterate what the questions that we're going to be considering are. So first is the forward problem. Give me a convex body. Can I try and find out what this Ex is in some sort of, elegant way? Is this possible? Then, spoiler alert, yes, this is possible. You can get sort of quite neat answers if you're happy to accept series and integrals, but you can write it down in a nice way. And then the second part is the inverse problem. Give me a function of relative angle. Is there some way that we can construct a shape which has this as its excluded volume function? And again, spoiler alert on this one, the question of existence is quite tricky. Trying to find something explicitly is quite tricky, but what we can do is write down an algorithm which will give us a best approximation. And that's what I'll be getting to at the end and show you some hopefully nice pictures. So just to reiterate, in this talk I'm only going to be considering 2D systems, and the reason why 2D is very, very nice for these problems is really twofold. The first is that the space of relative orientations in 2D is straightforward. It's just angles. These are a nice group. If you're in 3 dimensions, then the space of rotations, i.e. the relative angles in 3 dimensions, this is a sort of complicated object just from an algebraic perspective. And the second thing that makes life a lot easier in 2 dimensions is the fact that area is a kind of quadratic object, whereas volume is cubic, and quadratic things are much more amenable to Fourier methods and things like this. And these are the kind of things that we'll be exploiting throughout all of this work. So to go to the forward problem, the first thing that we're going to want to do is find a way of describing our convex bodies in a way which is amenable to this kind of analysis. And there are all sorts of different ways of describing a convex body, and the way that is very useful for these kinds of techniques is to consider the support function. So for those who haven't seen it before, you can define the support function in this way. So curly M, once again, is going to be a convex body in 2 dimensions. And you can define it as a maximum for every theta. So u theta will be the unit vector with angle theta. And then you just look at the maximum over all points in your body dotted with this. Now this might seem like a very strange thing to look at, but it has a very nice geometric interpretation. So if this is your convex body here, this sort of potato object that you have, if you construct some vector u, and then you try and drop a tangent plane onto it, then the support function of this angle will be this perpendicular distance of the tangent to the origin. Okay? And really, the support function is just a way of encoding the fact that if you have a convex body, you can just write it as a union of a load of half spaces. So if you were to think of a polygon, somehow a support function is a sort of more continuum analog of describing it by its sides, whereas you might be more used to parametrizing convex bodies in terms of their boundary, which is kind of analogous to describing convex bodies by their, well, polygons even, by their vertices. So it's a kind of dual way of looking at it. And another way of interpreting this support function h is that it is the convex conjugate, or Fenchel conjugate, depending on your background, of the indicator function on your domain. One thing to bear in mind is when I say indicator function here, I mean it in the convex analysis sense, which is that this is a function which is 0 on your set and infinite otherwise, whereas PDE people might have it as being 1 on the set and 0 otherwise. But yeah, it's straightforward to go from the definition of this type of indicator function. You just take the Fenchel conjugate and you end up with exactly this expression straight away. So that maybe gives you a feel as to why this is a sort of natural way for convex bodies, because convex conjugation is, of course, very, very useful for convex bodies. And a convex body and its indicator function really are sort of equivalent objects. So given some function, will it or will it not be a support function? The general answer is no. So being a support function is really quite a restrictive condition. And in the case of twice differentiable bodies, then you are the support function of a strictly convex shape if and only if it satisfies this differential equality. And this is really just saying that the curvature is positive. I mean, that's one way of interpreting this. But the really key point out of this is that if we want to start talking about convex bodies and support functions, we have to really bear in mind that we can't just talk about any function. It's a pretty restrictive condition that won't always be easy to work with. And as I said, I mean, you may be more used to describing convex bodies by parametrizing their boundary. There is a straightforward way to go from the support function to the parametrization of the boundary, which is by this relationship here. So u theta is the vector in the direction u, and then u theta prime is the orthogonal direction. Okay. And so as I say, these are very, very nice things to play with if you're going to be talking about convex objects, and certainly for the problems that we're going to look at today. And the reasons are down to just a few little equalities. So the first is that if you have two convex bodies, then the sum of their support functions is the support function of their sum. This is a kind of linearity, and again, summation of sets here is just taking the sum of all pairs in respective sets and making a new set out of these sums. Okay, so this is really a sort of linearity condition for support functions. The second is that it works well with rotations. So if omega is an angle, r omega is a rotation about omega, then you can just rotate the body and pull this into the support function itself. And a sort of topological thing that the support functions pick up is that if you have uniform convergence of your support function, this is equivalent to convergence in Hausdorff metric for your convex bodies. So you can sort of glue a few of these things together, and if we recall, m minus the rotation of m, this is the space which is inaccessible to the center of mass. We can use these qualities, plug it into this expression here, and we get a very, very simple expression for the support function of the exclusion region. And the aim now is to use this to try and work out what the actual excluded volume or area is in this case. And we happen to have some very nice formulae. This is one of several ways of writing it down. So we can write that in general for a convex body with support function h, we can write the volume as just an integration essentially of the thing against its curvature. Okay, so as I said before, this is really the curvature of the convex body, and you integrate the support function against it. So going back to the expression that we have for the support function of the exclusion region, we can plug this into the expression that we have for the area of a general body. And after a little bit of playing around, we can write it as this sort of convolution type object. So we get twice the area, then we have the curvature again here, just like we did here. But then we also say have this sort of convolution-like perturbation by theta here and here. Okay? And this formula, again, it may not be completely useful, but it's something that you can still put into a computer, and it admits a very nice representation in Fourier space. So if you just replace h, or write it out as a Fourier series, then it has this other expression on the top. So to try and give you an idea of where the things come from, so this one here really corresponds to the volume here. This one here, corresponds to this. Then the 1 minus n squared, this is really h plus h prime prime in Fourier space. And then this sort of shift of the Fourier coefficient, shift of your function, then becomes represented in this expression here. So what we have is that if we have the Fourier expansion of the support function, then we can very, very quickly and easily get the Fourier expansion of the excluded volume. And typically when people are using Onsager type models, they only ever really consider low-order Fourier expansions of the excluded volume anyway. So this really allows us to go back between the body and the support function, vaguely speaking, in some senses. But the big point being, we have now some way of computing this in a way that you can just throw it into a simple numerical integration scheme. But before really saying anything else, we should just look at this formula itself and say, what can we draw from this? So as I say, this is really a way of doing a Fourier expansion of the excluded volume itself. I mean, we have some cos n theta and constant terms, but really you can take the Fourier series of this expression very, very simply. And what we can do is just use the uniqueness of Fourier expansions to say, okay, if two functions have the same excluded volume function, what does this mean about the bodies themselves? And the answer is not as much as you'd hope. So what you would really, really like is that if you had two bodies with the same excluded volume function, then they should be the same body, maybe up to a rigid motion. But this isn't true, because what you can see is that the way that the Fourier coefficients of the support function appear is only ever by their absolute value squared. So if you perturb the phase of the Fourier coefficients of your support function, you don't change the excluded volume. And this really gives you a non-uniqueness that appears in this problem. So what I have here is a selection of shapes. These are part of a continuous family. So I took a function whose support function has two non-zero Fourier nodes. You can perturb the phase of one of them against the other in Fourier space, and depending on how much you change the phase, this is what this omega is here. So you have a bunch of bodies which are not equivalent as rigid rotations, but they all have the same excluded volume function. And somehow the fact that you're changing the phase of the Fourier coefficients, somehow you can see that you're sort of rotating part of your body as you're putting it into this kind of shape. Okay, so you can almost see it's twisting in the same way that the Fourier coefficients are being twisted in Fourier space. Right. Oh, and so one problem actually that should be mentioned on this is there is a little snag with that problem, which is that you may over-twist your Fourier coefficient and then stop being a support function. So if you're a support function for some phase of your Fourier coefficients, that doesn't necessarily mean you will be for every phase. You could sort of perturb things and then break this differential inequality which needs to be satisfied. Okay. So we have some way of computing the excluded volume. Now we can try and say, okay, if I know how to find the excluded volume, is there some way of finding the body? Now immediately we see a problem because we're not going to have unique solutions. I mean, that was what this example before said. So really this is, before we've even started, an ill-posed problem. But we can try and do the next best thing. So the first attempt that one might make is to say we have this expression for the excluded volume in Fourier space. If we have the excluded volume, we can try and rebuild our support function from this. So if you go through, you could just essentially integrate all of these against various cosines, and then what you would have is a system which looks something like this. So you would have to have, essentially, if you ignore this e to the I phi n, this is telling you that the absolute value of the Fourier coefficients of h have to be equal to particular Fourier coefficients of a proposed excluded volume function. And then you have a degree of freedom in that the phase can do whatever it wants, and then you're still going to have this equality being satisfied. But on top of this, remember, we can't just have any function, we can only have support functions. And that gives us this differential inequality that would need to be satisfied. And when it comes to any sort of practical application of this, this really doesn't seem to be a useful way of solving the problem, because you have a sort of Fourier space thing here, and then a real space thing here, and going backwards and forwards between the two and making sure everything's like doing as it should be. I mean, it doesn't seem to be possible outside of the cases when this is mostly zero. You know, if the Fourier coefficients of your excluded volume are typically zero, then you might be able to just tweak the phase of the coefficients until you get something which works. But in general, this isn't a very good systematic way to approach the problem. So the way that we're going to do this is a completely different way. So we're going to look at discretizing the problem and then trying to find good solutions in a finite set. And in order to discretize the problem, we're going to look at what are called zonotopes. If you haven't come across them before, they're essentially a parallelogram with more sides. So if you have a parallelogram, this is just the sum of two line segments. A zonotope is a sum of at least one line segment, okay? So we have an example here where we take three line segments, we take the Minkowski sum of all three of them, and we end up with this six-sided head-to-tail symmetric body. Now, in 2 dimensions, being a zonotope is equivalent to being a head-to-tail symmetric polygon. So we're not going to be able to look at things that don't have head-to-tail symmetry, but we'll call this a good first attempt at least. So why might zonotopes be a good object to deal with when we're looking at this kind of problem? Well, the first is that you can find their perimeter and volume incredibly easy. So because you can really chop up your shape into smaller parallelograms, so this parallelogram is spanned by this vector and this one, this parallelogram is spanned by this vector and this one, and so forth. So by chopping up your shape into smaller parallelograms, you can work out the area very easily by this expression here. And similarly, for the perimeter, you see every vector counts twice, once here for this one. For the long one, it counts here and here. For this one, it counts here and here. So the perimeter is just twice the sum of the lengths. So, okay, that's great. We can find their volume, we can find their perimeter. But the thing that we're really going to find useful when looking at excluded volumes is that they also work well with summation. So if you take the sum of two zonotopes, then what you get is just the zonotope spanned by putting the two lists of spanning vectors together. Okay, so this symbol here, I'm just saying I take the list of spanning vectors for one and I stick on the list of the spanning vectors for the other. So again, these are something which work very, very well for the type of problem that we're looking at. And so in general, what we can do is we can write out what the excluded volume for a zonotope is. So what I've used here is the notation that for each vi, which is going to be in the list capital V, it has its absolute value, which is norm vi, and it's going to be at angle theta I to the x-axis. So the angles appear within our formulae, and then the lengths appear in the formulae here. This is all looking good. And this is, again, something that you can explicitly compute given a finite list of vectors. But also, because the way that the theta, which is the relative angle of the two bodies, appears, is in an absolute value of sine something, this is again something which is very amenable to Fourier techniques. Okay? There's no reason why you can't just take the Fourier series of this. And this is what this expression here is. We only get the even coefficients in cosine. And the constant term is given by twice the volume plus this factor of the perimeter squared. And the Fourier coefficients themselves are given explicitly by this finite summation here. So what we have is the lengths appearing on the outside twice. This sort of makes sense because of the homogeneity of area. And the relative angles between the line segments appearing inside this cosine term. Okay. So what we can use is try to do a sort of least squares approximation of a proposed excluded volume function using this Fourier approach. So you give me some function f, this is the thing that we want to construct the excluded volume of, and then, so this is little f by the way, not to be confused with curly f. Now we have some input parameters, so we're going to have little k, which is the number of line segments, or equivalently half the number of sides of the proposed zonotope we're going to be using, and m, which is kind of a regularization parameter. And then we're going to be minimizing an objective function over lists of k vectors, so we really have 2k variables. And the objective function is going to be the L2 norm of the projection onto the first m Fourier coefficients of the difference between the excluded volume and f. Okay? So if we didn't have this Pm here, so if we just looked at the L2 norm between the excluded volume and f, the problem is we're going to have infinite sums turning up all over the place, which is going to make things complicated. So we do the projection onto the first m Fourier coefficients just to turn all of our sums into finite sums. Everything becomes algebraic at this point. So using the expressions that we had before, we can rewrite this norm, remembering that if we have the L2 norm in Fourier space, we can just write it essentially as the sort of L2 norm of the Fourier coefficients. We have that this is really the constant term that appears in our Fourier coefficient, Fourier series, and then the higher order Fourier coefficients, so this would be the Fourier node of m, and the same BMs that appeared in the previous expression, which, just to rewrite here, are of this form. So we have a finite dimensional problem. Okay, it may in principle be very big, but finite dimensional. And this is really just an algebraic problem, because these are just scalars, these are just scalars. This is something which you can just throw into an off-the-shelf numerical solver and get some answers. But before throwing it into an off-the-shelf numerical solver and trying to get some answers, we should really check that we're going to get something meaningful that comes out at the end. So just to summarize the sort of convergence results that you have on this. So the first is that if you have a collection of minimizers, your k, which is the number of vectors that you're considering, goes to infinity, and m, which is the number of Fourier coefficients you're considering, go to infinity. Then you can always find some subsequence of your minimizers of this sequence, which will converge to some head-to-tail symmetric convex body in the Hausdorff metric. The excluded volume of these reconstructed shapes will converge to the excluded volume of your limiting shape in all sorts of topologies, including but not limited to strong W1P for p less than infinity, and weak W1P for p equals infinity. Or weak star, sorry, that should be a star there. And while you may not be able to completely reconstruct the shape, it may be that a solution doesn't exist, what you will always have is that your limiting shape will be a best approximation to f, its excluded volume will be a best approximation to f in the class of head-to-tail symmetric convex bodies. So what this really tells you is that if your f can be written as an excluded volume function, you can find a body which has it as its excluded volume function. And even if a solution doesn't exist, you can find the next best thing. And furthermore, we can put a rate on this convergence. So what we have is that if you have a solution, then you know that the error between the reconstructed excluded volume and your target function is going to be bounded by something of this form. So just looking at the three terms in this, what this is telling you is that you want k to be big, which makes sense, and you want m to be big, which makes sense, but also that if you have higher order Fourier nodes in your trial function, you're going to have much slower convergence. Okay? And this is something which we'll see in the implementations as well. And so I won't go into the details of the proof, but I'll just give you some vague ideas on how this works. So in these sort of analysis type problems, the thing that you always want in the first step is some kind of convergence. And in this particular situation, what we have is that the global upper bound, or energy bound if you want to call it that, of the ejective function gives an upper bound on the perimeter. And in 2 dimensions, this gives you a Hausdorff compactness of your bodies. And once you have your bodies converging to something, it's quite straightforward to extract the norms of convergence that the excluded volume has. And this comes in a quite immediate way. The real trick is that you don't know what the higher order Fourier coefficients of the excluded volume are doing. So if we just go back to the objective function only controls the first m Fourier coefficients of the excluded volume. So we expect them to be doing well. But the ones that are higher order, they could be doing something crazy and ruining everything for us. But what you have is a uniform estimate of this form which can be shown, which is that the L2 norm of the remainder, so this is 1 minus the projection, can be controlled by something which is going to 0 with m and controlled by the perimeter. So the global bound on the perimeter really gives that this thing is going to converge to 0 and avoid giving you any problems. So now we've got the algorithm, we know that it's going to give us something hopefully meaningful. We can throw this into the off-the-shelf solvers and see what we get. So for the first example, I put in the trial function f of this form, so 2 plus sine squared over 2. Now the reason I chose this one is twofold. One is that this has only got its first even Fourier coefficient non-zero. So by the estimate we had on the convergence, this should be converging very quickly because it doesn't have the higher order Fourier nodes. But as well, you can also write down using the forward formula that this is the excluded volume function of a very, very simple shape. I mean, its support function is basically, I forget the constants, but I think it's 4 plus sine 2 theta, or something like this. So for various values of k and m, so remember k is the number of vectors we use, m is the number of Fourier coefficients we want to match. What we have here is the excluded volume functions shown on the interval 0 pi. And I don't know if you can see, especially if you're at the back, but the trial function is the dotted brown line, and the reconstructed function is the blue one, which is a bit more angular. And the epsilons here, these are the relative L2 errors of the excluded volume to the trial function. And so what we see is more or less what we expect. You don't really need m to be that big, because remember, m is the number of Fourier coefficients, and we can match it very early. But once you have a decent number of vectors, you can get very, very accurate very, very quickly. Okay? And this really does look a lot like the shape which it should be converging to, except it's a bit too pointy on the ends. So this is a kind of nice example where everything does everything that we want it to. So a messy but not awful example. We have the trial function given by the absolute value of sine theta minus cos 2 theta over 2 plus 2. So why was this chosen? This was chosen because it has very high order Fourier nodes. I mean, this absolute value of sine means it's not going to be C1 at certain points, which means it's going to have very slow decay of Fourier coefficients at infinity. And also, this minus cos 2 theta means there's no obvious shape for which this is the excluded volume function. So what we expect to see here is maybe it will converge to something, but maybe it will do it slowly. And this is exactly what we see. Our errors are higher, but it definitely seems to be settling down to this kind of half-curved rectangle type object. Okay. And finally, we have the bad example. So this is 1 plus sine theta to the power of 30. The reason why I chose this one is because you can prove that this is not the excluded volume function of any convex body, which is essentially you can show a kind of reverse Sobolev kind of inequality for excluded volume functions, which is essentially something I forget off the top of my head. But you can show that the gradient has to be somehow bounded by the function itself, and that doesn't hold for this function. As you see, it's got a sort of quite big peak, so you can imagine that this isn't satisfying such an inequality. But as we expect, we have that this converges to something, and allegedly the solutions should converge to something which is the best L2 approximation in the admissible space. So as you see, very, very different. If you can see the dotted brown line, it's very far away, but this should be a good approximation of the best thing that you can have. Okay, so to conclude on all of this, So as we've seen already today, if you have a dilute system of hard particles, then the pairwise excluded volume is the key concept. This tells you about the low order behavior of the energy and of the pressure in the equation of state. If we have a 2D convex body, then we can compute its excluded volume using either Fourier or convolution methods, whichever you prefer. But in order to try and do the reverse process, you're going to have problems. First of all, because solutions are not unique. However, we can try and find a sort of best numerical approximation using algorithms which can run pretty efficiently. So one thing that I didn't mention, I'm not a numerics person. I coded this up and it ran in about 5 minutes on my computer. So actual numerics people that know how to optimize could probably get much better behavior than that. So I would like to spread a few thanks to people who proved very useful while doing this work. So this was done while I was in Peter Palfrey's group, and also Xiaoyu Zheng at Kent State University. And Epifanio Verga as well was involved in a lot of the collaborations that we've been having talking about free volume. And Mark Wilkinson, who was the one that sort of pushed me in the direction of looking at the inverse problem that appears on this. Okay.
Thank you, James. Do we have questions? Yes.
So first is I have two questions. First is a technical question. So you had two different Fourier methods. First one you didn't like very much, and the second one was for zonotopes, I guess.
Yeah.
So you never told us if there was any relation between the two methods.
Oh, so yeah, you can. There probably is actually. I haven't thought too much about it because it's quite messy. But the support function of a zonotope is essentially a bunch of absolute value of sign type things. So there probably is some link between the two of them, but I'll confess I haven't looked at it hard enough to answer your question properly.
Because you were kind of stuck on the first one. I thought that maybe the second one could help a little bit. My second question is, of course, the convex case is very interesting, more interesting from liquid crystal viewpoint, but from general physics viewpoint, the non-convex case is awfully interesting too, especially when the bodies can fit together in some way, or even better, fit together in several different ways. So what do you think the prospects are for understanding this in those cases?
I mean, so the forward approach, this really was using a lot of techniques from convex analysis. So that one, I think, could be quite tricky. They have this notion of polyconvexity in convex analysis, which is different from what you would call polyconvexity. It's the union of finitely many convex bodies. So, for example, a semicircle, like a semicircular arc, is not polyconvex, but an L shape is. It may be that in this sort of restricted class you can say something, but that's still beyond what I know how to do. For the zonotopes type approach, this is something that would possibly be much more amenable to non-convex bodies, but I think it's all about putting it in the right language, and then hopefully things fall quicker afterwards. But so yeah, at this point, I'll decline to answer more than that.
Very wise. Other questions? I think I must sum of the point with the forward problem. You had a shape and you rotated it a bit and there was a support function, and then eventually you rotated it too much and there wasn't a support function.
So in that particular example, that one always was a support function. But there are other examples you could write. So for example, in the paper that that's all based on, there's the example of an ellipse with aspect ratio 3, I think it is. And they have similar perturbations which produce bodies with equivalent excluded volume functions, but you only can perturb in phase something like pi over 4 or something like this. And then afterwards you end up with a negative curvature region. So sometimes it does work, sometimes it doesn't, which is why I said it's very ad hoc and not very good for a systematic approach.
Any more questions? Well, if not, I'd like to thank Jamie very much.